Okay, so today I'm going to do the very first one of these where we're going to go ahead and take a look at some released AP questions and kind of just go through as a process. I know some of you will be taking the AP test, some of you are not choosing to do so, but either way, it doesn't matter because really the AP test is a good way just to know if you actually know the material that it is that we're doing. So I picked out a couple of thematic ideas that seem to be repeated frequently in all calculus classes. And so the first one that I wanted to look at is just look at rate of change and how a story can be told through calculus. And we're going to start with the 2014 question number 1. And I'm going to kind of go through that process. We have another one that I'm going to do in the next video, and then I'm going to ask you guys to actually submit what you were able to come up with on one question of your own that will be your assignment. So if you could watch the first 2 videos to get a little bit of a flavor on how that works, we'll kind of see how things go. So here we go. I'm going to go ahead and turn on my ImageMate and let's see how this goes. Okay, so our first question says that we've got the grass clippings are placed in some kind of a bin for a period of time here. And it's defined by this exponential equation. And you'll notice this 0.931 here means that would be an exponential decay story, where it's in pounds measured and time is in days. So the first thing that I see in this particular problem is it talks about the average rate of change. And so we might recall back from the beginning of our course that average rate of change is basically our slope equation, f of b minus f of a over b minus a. And they're specifically saying on this interval from 0 to 30. So we're going to look at a of 30 minus a of 0 over 30 minus 0. And notice up at the top, it says this is a graphing calculator is required. So in this particular situation, I wouldn't actually do these calculations by hand. I would literally type this a into my y1 and allow my calculator to do the mathematics on this. And depending on how you set your calculator up, you're either going to get 0.197, or if you, instead of rounding, if you simply truncate, you would get negative 0.196. And this would be in pounds per day. So again, as stated before, I would just have this as y1, and I would just use the value feature of my calculator to do these, and I wouldn't even list what I'm doing here. I'm just going to show this minimal amount of work. Now, for the second part of that question, it says, let's find a prime of 15. Now, again, just like before, a prime of 15 on a calculator allowed question, I can just literally just say that a prime of 15 is equal to negative 0.164. Or again, if you use the truncated value, you could use negative 0.163. Now, you don't need to write this on the AP test, of course, because this is calculator speak, not actual mathematics, but I would just use the end derivative. I believe we would go paren y1 comma x comma 15. So if you didn't remember exactly how we actually found this value, that's literally all we would have to do for that portion of this question. Now, moving to part C. They go on in part C to ask, I can't get this paper apart here for a second. There we go. Okay, find the time at which the amount of the grassing in the grass clippings is equal to the average amount of clippings. So the first thing that we would want to do is we actually need to go ahead and find that value. So what we're going to do is the average value is 1 over b minus a, integral from a to b of f of x dx. Now remember, this was the area, this was the base, So if you took the area divided by the base, you would get the height of a normal rectangle. And so in this case, that would be our average value. So I'm going to do 1 over b minus a, which is 1 over 30, integral from 0 to 30 of a of t dt. Now again, this is a nice simple little idea because I then could go ahead and just set this straight into my calculator. And I don't have to do that mathematics. I can just use the numerical version of the integral on this thing, and I get 12.415 pounds. And again, that's as much as we have to do for that particular portion of this question. Now we get to our last part, part D, which says, when you move above 30, let's go ahead and let this L of t be the linear approximation. Now, normally we would call this linear approximation y, but instead of calling it y, I'm going to call it L of t. At 30 is a better model for the grass clipping, so they're thinking that a linear approximation would be better than the exponential they previously used. And then it says, let's use this to predict what happens when would it be 0.5 pounds? So let's start there. So recalling back historically, we use this kind of point slope form of an equation. And as previously stated, I said I'm going to go ahead and instead of calling this thing y, I'm going to call it L of t as they said. Now the point that they're saying is a of 30 was, let's see, that was 0.783, and a prime of 30 is negative 0.055. Now each of these values would be found using our calculator. Again, a was, we probably put that in y1 earlier. So if I do go ahead and do y minus the y value, 0.783, equals m, which we have right here, negative 0.055 times x minus that x value, which of course was 30. Now, of course, I probably should have used the letter t right here instead of x, because this is supposed to be referring to time. And so this is actually a really good linear equation. That's the linear approximation they were asking for right here. And then the last little part is they're asking if L of t equals 0.5, then I want to go ahead and set L of t equal to 0.5 and go over here and solve for t. And that's actually a fairly simple little thing to do. So I've got 0.5 minus 0.783 equals negative 0.055 t minus 30. Go through and do a quick solution on that. Again, they're not particularly worried about seeing your distributive property and all of that, but you would get t is approximately 35.054 days. All right, and that kind of sums up that first question. You can see we've done a fair bit of math. We've looked at average rate of change. We've looked at a numerical version of the derivative from our calculator, and done average value and a little bit of using the derivative to find the slope, and using that slope to come up with a linear approximation. So hopefully that made sense, but that was the first example of that, and I'll be putting up another one as well. Thank you.